Hi, in this video we will discuss case study 3. This case study 3 is covering chapter 5, shear and bending moment diagram. The problem given in the case study 3 is shown in this figure. We need to draw the shear and bending moment diagram for the beam and the loading shown, and we need to determine the maximum normal stress due to bending. To answer this kind of problem, we need to list all of the known given in the question. We have the type of the beam, the wide flange 310 times 60 with Sx equal to 844 times 10 cube millimeter cube. And we have the dimension of the system. The strategy used to solve this kind of problem is drawing the FBD and calculate the reaction forces. And then the second, we need to create the shear force diagram or SFD using a partition method. And the third one is by defining the bending moment from the SFD. Then last one, we need to find the maximum absolute value of M. The first step that we need to do is drawing the free body diagram. This is the free body diagram of the system. And because of hinge at point B here, we can separate them into two different beams. So we have two different sections of beam. And also, because of the hinge at point B, we have a reaction forces at point B. The reaction forces is acting like a pin, where there is a reaction in x-axis and y-axis. But for this case, because there is no external forces acting on x direction, we can assume the reaction at x direction is equal to 0. Then we go to the first section of the beam. We already neglect the reaction forces at x direction, so there will be only reaction forces at y direction. There is a reaction force at A and reaction forces at B. We can find the reaction forces by using a moment. Now we're using the moment at A equal to 0. Then we can obtain the reaction forces at B and Y direction. And it is equal to 96 kilonewton. After obtaining the B, we can use the sigma forces at Y direction is equal to 0. And we will get RA in Y direction is equal to 96 kilonewton. After obtaining the reaction forces for the first section, we go to the next section. It is the same way, where we need to find the reaction forces at C and E by using a moment. Sigma moment will be equal to 0. And we will obtain that the reaction at point C in Y direction is equal to 248 kilonewton. Then by using the sigma Fy equal to 0, we will obtain the reaction forces at point E, which is equal to 56 kilonewton. After we obtain all of the reaction forces acting on the beam, we can create a partition to find the shear stress in the beam, or V. On the first section, we create a two partition. The first one is right just after point A, and the second one is just before the point B, or we can call them as VB1. After we done create the partition at first section of the beam, we go to the next section of the beam. If in the previous one we starting from the left to the right to create the partition, now in the second section of the beam we start from the right to the left. So we start from the third partition is right before it is reaching point E, or in the left part of point E, and then the second partition is on the right part of point D, or it is called as D2 because it is on the right part of point D. And then we continue to create the partition. Now we have the fifth partition and the sixth partition, where it is on the left part of point D, or we call it as a VD1, and it is on the right side of point C, and it is called as VC2. And then we can continue to create the partition. It is on the left part of point C for the seventh partition, or we can call it as VC1, and it is on the right part of point B, so we can call them as VB2. After we create the partition, we can calculate the V based on the partition that we have created. For the first partition and the second partition, we will obtain that the VA is equal to 96 kN, and for the VB1 is equal to minus 96 kN. And then we go to the third partition, the fourth partition, and the fifth partition. It is the same way how to find the V on the beam. Minus 56 kN for the VE, and we have VD2 equal to minus 56 kN. Then VD1 we will obtain 104 kN. Then we go to the sixth partition, where we need to find the VC2, VC1, and VB2. The sixth, seventh, and eighth partition. For sixth partition or VC2, we will obtain 104 kN, and then for the VC1, we will obtain minus 144 kN. On the next partition, we will obtain minus 96 kN for VP2. After calculating all of the shear based on the partition that have we create, we can go through to create the shear force diagram. This is the partition that have been created. The shear occur in this beam is VA equal to 96 kN, VP1 minus 96 kN, VP2 minus 96 kN, VC1 is minus 44 kN, VC2 is equal to 104 kN, VT1 104 kN, VT2 is minus 56 kN, and VE is equal to minus 56 kN. So we can create the FPT here. So we have the VA on the first partition here, and then we have VP1 and VP2. Then we have the VC1 and VC2. Then go through the D1 and D2, and then this is the point E. After we create the shear force diagram of the system, we need to find the intersection point here where it is reaching 0. We can use a congruence and similarity theorem to find the distance from point A to point F where it is intersecting the 0, and we will obtain 1.2 meter as the distance from A to F point. Then we can calculate the areas below the graph to find the moment acting on the beam. We can find the area below the graph. From A to F, we can use a triangle formula to obtain the area below the graph. It will be equal to 57.6 kilonewton meter, and then from F to C will be equal to minus 129.6 kilonewton meter. From C to D, we can use a rectangular formula and it will give us minus 156 kilonewton meter, and from D to E will give us a minus 84 kilonewton meter. From the shear force diagram that have been created, we can create the bending moment diagram of the system. Then for the value of the bending moment, we can obtain from the calculation that has been done before, such as MA equal to 0. We have a 0 at this point. Then from A to F, we have a 57.6 kilonewton meter for the area below the graph, and it will be the value at the point F here as the peak, which is 57.6 kilonewton meter. Then from F to C, we have a minus 129.6 kilonewton meter as the area below the graph. But for the bending moment diagram, we need to add them up. From minus 129.6 kilonewton meter will be added by 57.6 kilonewton meter, and we will obtain a minus 72 kilonewton meter at point C. And then from C to D, we will obtain a 156 kilonewton meter. Then the same thing goes as before, where it is summed up from the previous value. So it will give us a 84 kilonewton as the moment acting on point D. Then from point D to E, we have a 84 kilonewton meter as the area below the graph from point D to E. Then we add them up and we will obtain 0 moment at point E. From this bending moment diagram, we can see that the 84 kilonewton meter as the maximum M. So we have the maximum moment occurred in the system is equal to 84 kilonewton meter. So for this beam, on the wide flange beam, the forces is acting on the Y direction. So we will use the XX direction to obtain the data from the table in appendix. In the problem, we need to use the designation for W 310 times 60. So we will take this row. Then we need to obtain the SX data on axis XX. So it will give us 844 times 10 cube millimeter cube, or it is equal to 844 times 10 power minus 6 meter cube. The maximum stress that might be occur in the beam is calculated by this formula. And by substituting the value into this formula, we will obtain that the maximum stress occurred in the beam is equal to 99.5 times 10 to the 6 Pascal.